one must be careful in multiplying matrices. To multiply a matrix A to a matrix B and obtain the matrix product AB, the number of columns of A must agree with the number of rows of B. Okay, so if A is M by P, then B should be P by N, and the product AB will be the M by N matrix whose entries C sub ij satisfy this rule. Observe that in this formula, we have the entries AI1, AI2 up to AIP, which are nothing but the entries in the ith row. Okay. And similarly, the entries B1j, B2j, up to B sub pj are the entries in the jth column of B. Now, if you are familiar with the concept of dot product operation with vectors, the entry Cij is obtained by taking the dot product of the ith row of A and the jth column of B. Note that if A is a square matrix of size n, then we may multiply A to itself as much as we want. And if, say, we want the product of A with itself 2 times, okay, then we will simply write the matrix product by A raised to P. So we can actually perform matrix exponentiation if A is a square matrix. To illustrate the rule that we need for the matrix product, let's consider this. Suppose we have matrix A and matrix B, and the matrix product AB will have entries Cij satisfying this rule. If we are to find C11, okay, so what we do in this rule, we take the first row and the first column, first row of the first factor and the first column of the second factor. Okay. So then multiply respective entries as is indicated in our rule. That produces C11. So to find the entry in the product that lies in the second row and last column, then we have to take the second row of the first factor and the last column of the second factor. So applying this formula gives the desired entry in the product. So here are some examples. Suppose we have matrices A, B, C. A is 3 by 2, B is 2 by 3, and C is 2 vector. So first, we observe that the product of B and C is undefined because B has 3 columns while C has only 2 rows. The number of columns of the first factor does not match the number of rows of the second factor. But BA is actually defined. So B has 3 columns, A has 3 rows. So this product is well defined, and following the rule, BA should be a 2 by 3, rather a 2 by 2 matrix. Okay. So we compute the 4 entries now in BA. So the first entry is obtained by taking the first row of B and the first column of A, then multiply respective entries. That will give this expression, which equals 4. If you want the 1, 2 entry in BA, we take the first row of B and second column of A, then multiply respective entries and add the results to get negative. And the rest of the entries are obtained in a similar fashion. So VA is the 2 by 2 matrix for negative 2, 6, 16. Note that AB is also well defined because the number of columns of A, which is 2, agrees with the number of rows of B. So from our definition, the product AB should be a 3 by 3 matrix, and you can check that the entries in AB, okay, so you can check that the matrix in AB are as shown, it's equal to this matrix. What is important to observe here is that the result that we obtained for AB is different from the one that we obtained earlier for BA. So this tells us that unlike multiplication with usual numbers, matrix multiplication is not a commutative operation. Okay? In other words, the order or placing of factors is very important when we write matrix products. You can also check that the product AC is well defined and the result is a 3 vector, or a 3 by 1 matrix. But CA is undefined because C has 1 column, A has 3 rows. Earlier, we saw that we saw these representations in terms of matrices for this system of linear equations. Okay, so you can write it as a matrix equality, and then one side can be written as a matrix sum, and you can simplify it further, write it further as a sum of 2 scalar multiples of 2 vectors. In fact, we can simplify further this left-hand side of the equation. You can write the left-hand side as a matrix product, wherein the left-hand side involves a 2 vector, rather the right-hand factor, okay, involves a 2 vector consisting of the variables x1, x2, and the left-hand factor is a 2 by 2 matrix consisting of the coefficients in the linear system 1, negative 3, 2, 1. And this observation can be applied to a general system of linear equations. If we have a system with n equations and n variables, x1, x2 to xn, we can always write this system as a matrix equation in this form, wherein on one side we have an m vector consisting of the constants, so these, and on the other side we have a matrix product of an m by n matrix and an n vector. The n vector consists of the variables as entries, while the m by n matrix, which occurs as a left factor, then consists of the coefficients as entries.